Okay, can you see? It's kind of delayed, but it should pop up in a second. Like, you should be able to see this screen. Hello. Okay, audio's being ready. Hello. Okay, yeah, audio's working. At least that's what it thinks it is. Okay, let me get the slides and stuff. At least that's what it thinks it is. Oh, okay, we're good. It's just really delayed, but that's fine.
Should we have to like get close to the mic?
Yeah, definitely be really close to the laptop.
I don't want this
On the screen.
about the other mouse.
Oh, no, I don't.
So
Super Pro. I think you might need to sign back in the collab. Yeah, sorry, tell me your password real quick. Okay, we're good. Collab's here, slides are here. Let's put that up.
How do you want to make these screens different? That was fun.
Oh, yeah.
It's on the slides, right?
You put a tiny URL too, right?
Like people started out like right.
Oh, it's because you're on this laptop. That's why it's annoying.
Do you know about rank diffusion embedding? Do you know about rank diffusion embedding?
What is that?
Bro, I have to like review this paper and I'm like, I don't know any of this, bro.
Wait, so what do you mean? Is it like a
Okay,
research?
so is this the real one or is this
Yeah,
the
like
that-
submitted
the
a paper,
template is
so I have to like
This is the template?
This is the real one. Template
I
is-
think I've done those in like high school.
Okay, you probably need to sign in again over here, but let me put this presentation on the screen.
yeah.
Wait, is it just in? Sorry,
Yeah, Vardan was supposed to cover, but
Oh, it's already up. I'm tweaking. Oh, wait, never mind. I should switch these. This is what's on the screen.
Do we want the template on the screen? We want the template on the screen.
Okay, you want the reference with you. Okay, the laptop is you. That's the screen. Okay. Wait, template on the screen.
you really need to do it that way because like you'd have to like look at that screen to like
Let me see.
see like code. Could you just like switch out the tabs?
Well, this one's always going to be what's on that screen. That's kind of how it works.
Yeah, I know. I'm saying like, you put whatever's this tab on that and those two tabs on here.
Okay, but like this is what's going to be seen.
Yeah, that's what I'm saying. We want the template to be the same.
Well, that's the template.
Oh, wait.
Yeah.
No, oh yeah, never mind.
Yeah, you're fine. Yeah, okay. Okay. Yeah, we should
Probably
be.
name all of them.
This one. Yeah. Okay. This.
I should have wrote it down.
Where's the present button? Why is there no present button?
I think I've decided it.
I mean, you already have an account, so we're fine.
You have to give you permissions.
I think I should use it present.
Like, why is there still no present button? Why is this still there?
Because
No, that's fine. Okay, no, tweaking. Okay. You starting like right now, or do you want some more time still?
Let's just start right now.
Okay. Should be set to go. Do you need me to stay or do you want me to?
Let's I gotta do something with you.
Yeah, you can do it.
Okay, yeah. Just make sure.
Just like tell us what to do after.
Just press the stop streaming button and close the YouTube Studio tab.
Okay.
It should be fine. I'll be watching the stream. So. Oh yeah, you guys know what to do with the ads and stuff, right? At the end.
Yeah.
Okay. I realize that's picking up what you're saying also, but it's fine. Okay. Have fun. Yep.
You want to start?
The first you have to show topological.
Okay.
Alright.
Do you want me to do since I'll do the introduction? as well?
Yes, since you're the introduction, you start off, right?
Yeah, I'll start. Ready to start.
Hey everyone, we're gonna start now.
Yeah, so hello everyone, welcome to our computer vision workshop with OpenCV. So you'll see two links here. The first link is to our Colab template where you can actually interactively follow with us and type in code. And if you're stuck, the second link gives you a reference Colab where the code is filled in for you to view and also run. So when you guys all have the Colab up and running, we can start. So I'll give you guys 2 minutes or so.
Yeah, let us know if you're not able to access it. Shouldn't be able to.
Okay, can you guys just show me a thumbs up if you got the Colab working? Okay. Alright. Alright, so to get started, by raise of hands, I just want to know how many of you guys have heard about computer vision, the term, before. So by raise of hands. Okay, that's cool. I'll also ask a follow-up question. How many of you guys have worked with just image editors or just video editors, things like Photoshop before? Yeah, so with computer vision and OpenCV, we take it a step further by actually being able to automate such tasks that you can do in a common image or video editor. So to start off, computer vision is a field of artificial intelligence, which basically enables the computer to interpret and process virtual information similar to that of a human. And by analyzing the images and videos, the computer can recognize patterns, detect objects, and make decisions on what is actually seen. So there are many applications in computer vision. The three common examples of computer vision applications are in the healthcare, manufacturing, and automotive industries. So a healthcare professional may ask, how can we use medical image data to diagnose diseases more quickly? So in the healthcare industry currently, a medical professional will be able to get MRI scans or other sort of scans where you can actually detect diseases. And to automate these processes, it's very important that the actual patient gets that detection as quick as possible. So using computer vision and things such as neural networks coupled together, the healthcare industry is currently using computer vision to analyze this medical image data and give early-based detection for diseases and other signs or symptoms. Additionally, the manufacturing industry, they may ask, how can we actually determine defective products that are moving along a conveyor belt or being manufactured? So these specific objects may have some calibration issues, such as the dimensions may not be proper. There may be things such as broken parts. So using computer vision, we can also track objects over time and detect those objects and make sure that those objects are not being sent to whoever is the buyer. And finally, as you all know, there are many Tesla cars, there are many autonomous vehicles out on the roads today. And all of these autonomous vehicles require computer vision, as they require detecting objects on the road when you're doing lane changes or even trying to do things such as parking. So as we can see, these are just common examples for industries that use computer vision, and it has significantly enhanced the efficiency and accuracy for certain tasks in these respective industries. So in this workshop, we'll be going through OpenCV. So OpenCV is basically a computer vision library, an open source computer vision library that provides extensive tools for users to load, manipulate, analyze, and display visual data. So it enables users to manipulate the data, extract features, and also detect objects and analyze real-time video footage, making it very powerful for computer vision applications. And we'll be coupling this OpenCV library with Python. And if you guys want to get more information about the actual methods and the framework for OpenCV, the documentation is linked in this collab.
Alright, so now we're actually going to get into the code. First thing we're going to be doing is loading our materials or loading our images and videos that we'll be using for this computer vision workshop. So the code should already be set up for you. All you have to do is open this category right here. If you want to run code, all you have to do is press this play button right here. It should download it. So we can just click run cell or control enter. It'll take a little bit, but it should successfully download them as long as you're connected to the internet. So as you can see here, we were able to successfully, or I think it's still downloading, right? Oh no, it's successfully downloaded, right? So now that we've done that, now we're actually going to start with working with OpenCV with this data that we just downloaded. Alright, so before I get started, how many of y'all are keeping up so far? Have you guys been able to run that cell and download it? Okay, cool. Alright, so now getting started with OpenCV, the first thing we have to do is import our modules. So we're first going to be importing CV2, which is OpenCV. We're going to be importing NumPy, which is a Python data science library that will help us with some of our operations. And then we're going to be importing CV2 ImShow, which will allow us to show the images within a Colab notebook. Alright, so let's just run that. Alright, so the next thing we're going to be doing is loading our image, right? And so next thing we're going to be doing is loading our image. So as you can see here, we have this sort of like this placeholder here for our code. And the way we usually use Python libraries is by first calling the method and then dot whatever function we want to use. So we'll first start by getting our image by setting the variable image. And we'll set it equal to CV2, which is the library we just imported, dot imread, and we pass in the parentheses our image path. So image like that. And after we do that, let's just run our cell and load our image. So it should load successfully as long as you have the right image path, which you guys should. Alright, so now that we've loaded our image, next thing you want to do is resize our image, right? And I guess what is the reason for resizing our image? Does anyone have any ideas? Like why would we want to resize an image before processing it? Do anyone know? Well, the reason why we do it is because it's just faster, right? As you might imagine, having a lower resolution image is going to be much faster to process than, you know, something that's 4K or 8K, right? So that's kind of why we do it. So this will just help us with our making things more efficient. So let's just do that. So we're going to call this variable image again. When set it equal to, we call our CV2 function or CV2 library, and then we call the method resize. And after that, we want to set our parameters. So we get our previous variable image as our input, and then we want to set our new resolution, which is going to be 800 by 800, like that. So now that we have our image, now let's actually display it within our collab so we can all see it. So we can use the CV2 onShow function that we imported earlier, and then parentheses image. So let's just run that. And now we should have our image all displayed here, right? Alright, next thing we're going to be doing is learning how to grayscale our image. So this is just another process that we can use to help efficiently process our images whenever we perform image recognition. So we have our placeholder here, so let's just start with that. So let's create a variable gray. So this will be where we're going to be storing our grayscale image that we're going to be using. Set it equal to color CV2 library. And then we're going to be using the CVT color method, or convert color. So it's going to be CVT color, get our image, comma, and then it actually fills it out for us, but we'll just type it out anyways. So this will be CV2 color, CVT method again, and then color, and then BGR underscore, BGR2 gray. And this will apply grayscale to our image, right? And we have a few other processes here. This just allows us to convert our image to the proper grayscale format. And then what this is doing right here is just formatting. So we call this hstack function right here, and this just horizontally stacks our pictures so they look nice and neat. So let's just run this. Okay, so now, as you can see here, we have our earlier image that we downloaded here, and then now we have a grayscale image on the right side. Alright, next thing we want to do is learn how to blur our images. So the reason why we blur our images is so this is in the case where we don't want to capture all details of our images, right? So if we have like a really large image that we want to process, maybe there might be some details that we don't want to spend our time looking at within our image, so it might be better just to blur it just so it makes things easier. So let's just try to do that. So we create a blurred variable for our blurred image, call our CV2 method, and we're going to be using Gaussian blur for our blur method. Okay. Then we pass in our image variable that we processed earlier. we set our new kernel size or our new dimensions, so we'll just set it to 9 by 9 for now. And then we set this other parameter 0, and what this does is that it will automatically blur our image based on what we've set to it, basically, right? So it just automatically does the blurring for us instead of us having to define it. So if we were to define it, then we would have to set it to like whole variable, like 1 or 2. But for now, we'll just set it to 0. All right. So now let's run this. Oh wait, hold on. We also want to then stack our images using NumPy, just like how we did before. So we'll set another variable. We'll call this orig versus blurred. We call the NumPy function from earlier, then we use the hstack function. We get our earlier image and then the blurred image right beside it. And now let's actually run this. So this should show our previous image and then our blurred image on the right side. Yeah. So as you can see here, this image looks a little more blurred than the left side, which is what we want. So that will be useful. Alright, so now getting into more of the image recognition stuff, or one of the more popular functionalities of OpenCV.
I have a question.
Yeah.
How do you control the amount of
You just set this variable here, right? This parameter here. So I think if you do, I can try this, but I think if you do like, let's try port 5 for example.
Is it between like 0 and 1?
Is it 0?
You can set, so basically what's happening here is the kernel size, like the 9, it basically represents a 9 by 9 matrix used for the blurring, and the larger you make that kernel size, the more effective the blur will be. So if you were to change that to 3, the blur would be less significant. What the other parameter is doing, in this case the 0.5 or 0, is it's basically applying that blur to neighboring pixels. And when we set that equal to 0, basically based on what our kernel matrix is, our blurring matrix, it just automatically calculates it for us in OpenCV. So I'd say change the kernel size and you get difference in blur.
I guess it could be as large as the picture itself, so
Yeah, good question. So I'll just keep it like this, 0 for now. Alright. So moving on, now we're going to be getting into segmentation or edge detection. So what we're going to be doing is getting our previous image and then getting a new image with all the edges of our previous image. So how we're going to be doing this is like previous examples. We're just going to set a new variable. We'll call this new image edges. We'll set it equal to CV2. We'll call our CV2 function or CV2 library once again. Then since we're going to be using canny segmentation, we call our canny function. And then we want to pass in our grayscaled image, since that will make it easier for us to perform edge detection on our data. And then next thing we're going to be doing is setting our thresholds. So we'll set our weak edge threshold to be 50, and then our strong edge threshold to be 150. And what this basically means is that our weak edge threshold 50 basically means that edges that have a lower, I guess, strength than 50, we'll just ignore them. If the edge is greater than 150, we'll count that within our image. And if the edge is between 50 and 150, we'll see if that edge is connected to a strong edge, and if so, we'll count that as one of our edges that we'll track in our new image or our new edge detected image. Right, so let's just run this and it will show us. So we have a previous image there, and then we see a new image, and it looks kind of weird, but it basically just has all the edges of our previous image right there. And once again, this, as you might imagine, this will help us with image recognition, since we want to be able to see exactly what edges there are in our image, and this will just allow us to see patterns more easier, right? So that's the yeah. So okay, so we have these parameters here. So this 50 value is the weak threshold, and edges that are under the strength of the weak threshold are not counted within our edge detected image right here at the bottom. If it's over 150, we'll count it within our new image, right? If it's between 50 and 150, we'll count it only if that edge is connected to a strong edge. Does that make sense?
And is it like the color value of the gray value of, like, what's the 50, like, what's the edge value?
Basically, it's just the strength of the edge, right? So how prominent the edge is within the image. I don't know the exact. I'm sure you're looking for a more detailed description. I can tell you that. Maybe he can.
So I guess if you want to go more in depth with that, what's basically happening is, so have you heard of a gradient before, or like a change in values, right? So what's basically happening is, how the strength and the weak are happening is, it's basically figuring out intensities. Intensities are based on the brightness of the image. So based on the changes in the intensities, it's calculating a gradient. So those are what those edge weights basically represent.
So would like a colored picture would just be not so like prominent?
Exactly. We pass in a gray scaled image so that we we wouldn't want to use a colored image here. We want to pass in a grayscaled image.
Yeah. So when I mean strength, I mean like intensity. So, all right. So now, after that, let's actually apply face detection to our image. All right. So we kind of do this whole process over again. So we first load the image. We call that onRead function we used earlier. Right. And then we check if our image is loaded. We then convert our image to grayscale once again. And next thing we want to do is load our cascade model. And this is essentially the ML model we'll be using in order to detect the faces within our image. Okay, so to do this, call it a new variable, face cascade. We'll set it equal to, call CV2 dot, and then we're going to call cascade classifier. Call our CV2 method again, and what we're going to be doing is getting the model, the specific model we want to use for our cascade classifier. So we'll call CV2.data. So we're just getting the folder. Oh yeah, it should be cascade. So it should be HAAR cascades. So we're just getting into the directory of our cascade models, and then we're selecting this model right here. So har cascade. We're gonna find the frontal face model default.xml. So once again, this is just grabbing the file we want to use as our classifier model, right? Okay, so we make sure our model is running properly, and then next thing we want to do is actually detect the faces within our image that we just got. So we can do that by setting a new variable under here, faces. We'll set this equal to face cascade, the variable we defined earlier, dot call upon this model, detect multiscale, and then we're going to set our parameters. So we use our grayscale image. We'll set our scale factor to be 1.1, and then we'll set our minimum neighbors to be 5, right? So essentially what we're doing with this is that we're using a different scale factor in order to help us detect the faces within our image easier. And then this minimum neighbors is essentially it basically represents the number of times the face needs to be detected before being confirmed within our image. So as you might imagine, the greater our value here is, the more specific it needs to be, or the more higher criteria it needs to be for it to detect an image or detect a face. The lower it is, the less it'll be less. The criteria will be less specific, if that makes sense, right? So as you might imagine, the lower the number is, there's a higher chance of false positives. The higher it is, the higher chance of false negatives, or false negatives. So that's definitely something you want to, keep tweaking over time to try out different values to see what you get. And then last thing we're going to be doing is, so this model actually gives us the coordinates of our face. Now we want to actually put a rectangle on where it's actually detecting the face within our image, so we can actually see what the model is looking at. So we'll set this here. So we have a for loop. This essentially is the coordinates of our model, basically. So we have our x and y coordinates. These are the coordinates of the left corner of our or top left corner of our face, and then the width and height is the width. The WH is just the width and height of our face, basically. Pretty straightforward. So we'll call in our CV2 function again. Then we'll draw a rectangle with the rectangle method. We grab our previous image, get our coordinates of the top left corner, so x, y. We draw our rectangle, so this will be x plus w, y plus h. And then set the color of our rectangle, so this will be green, so we'll set that using RGB format. And then we'll set the thickness of our rectangle, so it's just B3. Alright, so now that we have all that set up, let's actually run this. And as you can see here, we are actually able to successfully detect where the face is within our image, and this is once again based on the coordinates from our model, right? So yeah, so that's pretty much it for the face detection part. Does anyone have any questions before we move on? Alright, go ahead.
So far, has everyone gotten up to here? Working fine? Okay. Yeah, so after we basically detect where our face in that image is going to be, we'd like to take it a step further and actually do a face recognition on the exact face. So what we're going to basically be doing is we're going to be importing a deep face pre-trained model. So what the deep face model basically does is basically it uses a convolutional neural network, and to not get too in depth with what's happening in there, what happens is basically based on the difference in intensities of just the image. For example, the difference between a person's cheek or an eye, those patterns are all recognized as the image is seen, and basically a feature vector is created. A feature vector basically converts our image data to actual numerical coordinates or numbers, and that feature vector is used to actually determine patterns. So I'd like everyone to first run this pip install deepface. It may take a while, but it should install. So it looks like it was successfully installed. And then what we're going to do is we're going to import modules. So from that deepface package that we just pip installed, we're going to import this deep face module, and then we're also going to import, yeah. You have an error? One of those in here. It is. Did everyone else get it to work properly? Okay. Alright, yeah, I'll just continue, just because this is a simple step. So basically we're importing the computer vision module, and then we're also importing the CV2 IMShow module as well. So now that our modules are imported, we can now load an image and view the results of this model. So what we'd like to do is, we're using the same image from the previous tasks that were used before, and we'll basically have a new variable called result, and then use the deep face module and call this method .analyze. This .analyze method will take in the actual image path and it will also take in specific actions that we want to predict. So for example, we'd like to feed this image in and see specific predictions for the emotion of the image, the age, and the gender. So when I mean the emotion, age, and gender, we mean the actual face that is involved in the image. And then we'd also like to make enforced detection equal to false. So what this enforced detection equal to false basically does is, what this model will do is if an image is not found, it will return an error automatically. So when we set this enforced detection equal to false, we're basically making this model persist through that operation and still try to find the face even if it looks blurry or even if it's having trouble finding the face. And then once we run this cell, so it should be running this for each of our actions, so for emotion, age, and gender. So eventually we get our results. So the predicted age is 32, the predicted gender is a man, and the predicted emotion is sad. So as we can see, the age is a bit off. This is Kobe Bryant in mostly his 20s. He's not 32 in this image. So this basically displays how intricate convolutional neural network models are, and it requires a lot of tuning, hypertuning, like parameters and weights. So yeah, if you guys are interested in that, I definitely look into like the deep face framework and also maybe try to build your own convolutional neural network for this type of task. And I mean, at least the predicted gender, the man, and the predicted emotion, I think sadness is somewhat okay for this. Yeah. Where's the presentation? Yeah, so this is our attendance for this session. If you guys would scan this and record your attendance.
Well, we're still not done. We're just having a quick break.
Yeah.
But there's no option for
The event
Yeah,
name.
we get it.
Hold on, give us a second.
I guess if you want to do like another little thing of code and then
Okay.
Yeah,
Yeah.
we'll just continue, and then at the end we'll show the arcade again, so you guys can actually scan it.
I mean you can just do like another block. Like,
Okay,
Just like-
just let me know if
yeah.
yes.
All right. So moving on. Now we'd actually like to verify a classification with another reference image. So the main goal of this cell would be we basically want to give this model a reference image so that we can see if the feature vectors can match, and that we can actually say that, yeah, this image is Kobe Bryant. So to do this, we're basically going to have the same result variable, or this is a different result variable that we're defining, and we're going to call the deepface module again with the verify method. And we're going to send in the first image path, which is our original image, and then the image2 underscore path will be our reference image. So after we do this, we should be seeing the reference image as well as seeing if it is Kobe Bryant or not. It's going to give us a yes or no. So this is the reference image that's fed in, and this is the model running. And as we expected, it says, is this Kobe Bryant? It says true. So this basically tells us that both of the feature vectors from that model were matched within a specific threshold. So now we'll go back to the attendance. If you guys want to try the QR code again.
We all able to sign in.
Okay, good.
Just keep it.
Okay. So any questions so far? Any thoughts about what we've done?
Can you go back to the code?
Yeah, I'll go back to
Let's go
it.
back.
Oh, now? All right. Yeah. Which part?
The last part.
This part? Okay. Yeah.
For the reference image,
Mhm.
is it, for the verify, does it automatically convert them to gray within the method?
Yeah, I think it will automatically convert to grayscale image for both, yeah. All right, any other questions, or are we good to move on? The next part is a different idea. So, okay. So now we'll get into object detection and motion tracking. Before we were working with images, but now let's see how we can actually use computer vision on video footage to detect objects and track motion. So we're going to import our modules. Of course, we've been using the CV2 for this whole workshop, the NumPy as well for data science operations. We're going to import time, and we're also going to import the CV2 time show as we've done in previous steps, and then import this from google.colab, import the files. This will be basically used to download our final video. So that's how it should be good to go. So now we're going to actually load in the video using OpenCV. The exact video here it's basically a video of a conveyor belt system in Changi Airport. So we'll load this video in by doing cap equals cv2 dot video capture. This should be a capital V. And then we're going to send in our video path. And once we run this cell, it should say that the video loaded successfully. So that's good. If you get video loaded successfully, the rest of the steps should work. Next, we're going to do something called background subtraction and removal. So to do this step, we're basically going to have this FGBG is equal to cv2 dot create background subtractor, and as you can see, this fills it in for us, MOG2, and then history equal to 500. We're going to set the variable threshold to equal to 50, and then we're going to set detect shadows to true. So what this background subtractor method is basically doing is we only want to focus on objects that are moving in the image, and there's going to be that specific background that we do not really care about when we're trying to detect the objects. And basically there are three specific parameters. So the history parameter is specifying the number of frames that we're using to actually identify our background. The variable threshold equal to 50. So what this represents is it is representing how when an object is moving, the variance threshold is basically saying detect this object based on sensitivity in the movement. So basically a larger value means that this background subtractor will be more sensitive to slight movements, while a smaller value will mean that it's less sensitive. And then detect shadows is set to true because there's going to be shadows in the video where we do not want to detect shadows as actual objects. So we make this detect shadows equal to true to remove that possible problem. So moving on, we want to set up the video writer as well. And to set up the video writer, we can have out equals cv2.videowriter. And then we want to have our file name called output.avi. And then this for cc, this is basically just setting up our video type. So we're sending it here into this video writer. And then we're having our frames per second, which is 20. And then the actual frame size will be 1280 by 720. And after we write this video writer, this is basically a check for making sure that the video writer is set up. And then we have these common parameters that we'd like to set up. Like we want to track the actual luggage positions, the stationary durations, and then we have basic parameters such as a stationary threshold. This basically represents the number of seconds it should take before we classify an object as non-moving or stationary. We have an area threshold of 2500, which basically represents the minimum number of area for that object to be represented as an object that's moving. We have the merge distance. We will get more into that in later steps, and then a dilation kernel is also used for morphological operations. And then we have the colors also set up with their respective codes in RGB. So once we run this cell, this should run through properly. And here's a function for merging boxes. So basically, when you try to detect objects in a video, there are going to be some areas where there's going to be multiple rectangles that are drawn on the object. And to try to reduce this error of having multiple rectangles drawn on an object, what this method is basically doing is we're taking the boxes and we're trying to create, based on the boxes that we have, we're trying to create boxes that are larger. And that one box will be represented compared to multiple small rectangles when we're trying to actually detect our objects. And we also are going to append those coordinates as well once we have found the merged boxes. So you should be able to run through that cell properly. And then we have our function for frame processing. So there are some morphological operations that we'd like to do, like fgmask is equal to cv2.morphology ex, and then send in our fgmask again and have cv2.morph open, and then our dilation kernel that we specified before. And then we're also going to have fgmask equal to cv2.morphology ex, and then fgmask cv2.morph close, and then dilation kernel. So what these two steps, there's actually a typo here, there should be fgmask. So what these two steps are basically doing is that one step is basically applying an erosion. So in computer vision, erosion is basically reducing white noise in an image and trying to shrink the image. And the second line of code is giving a dilation. So what dilation does is it enlarges your image and also fills in specific gaps or holes that may have been created by the erosion part of the code. And then we're going to also find our contours, and the contours are basically used for detecting boundaries. So we're going to have cv2.find our contours, and then our fgmask, our cv2.retr external. What this parameter is doing is it will basically retrieve the outermost contours, and then we'll also have a cv2 chain.approx simple, which basically is going to compress our contour points. And we definitely want to compress the points to reduce computational power. And then we're going to have boxes is equal to cv2.bounding rectangle with parameter c passed in, and we're going to have a for c in contours, and if the cv2.contour area c is greater than the area threshold. So what this is basically saying is we're going to create bounding rectangles for each of the contours if they're in the area threshold. So this line of code should have actually been for here. So now we can run this line of code, and it should run through. And then this function here is for basically tracking our luggage. So what's happening here is we're tracking and classifying luggage as moving or stationary. We have our initial parameters set up as our dictionaries to store our locations. And then we have this for loop, which is basically calculating the centers, storing timestamps, And then we're also finding the closest previous position within a small tolerance. We're basically using the previous centers because we want to track the object over time. So it's really important that we store these previous centers. And then we have this previous match center to track the actual duration. And these two if statements right here are basically figuring out if our box is a stationary box or a moving box. Or sorry, a stationary luggage or moving a luggage. And then we're going to also have this else statement here. If that center is, if it's a new object, then we're going to initialize the duration as shown here. And when you run through this, this should run through as well. And then putting this all together, what we do is we run a while loop. So while this video is running and while it's going through its duration, we're going to resize every frame. We're going to get the current time. And then we're basically going to send the frames over to this process frame method to get our merged boxes. And then we're going to track the luggage with the frames, the merged boxes, and the current time. And then we'll also do this to-do method here, where we're basically going to be writing the frames out to the video. And now when we run this code, too many values. Yeah. Which part? Which part?
Should be underscore by contours.
Oh, okay. Yeah. Alright. Yeah, there should be an underscore next to contours here. So make sure that you guys get that. And then just run through again. So what's basically happening is you'll be able to see each individual frame of this image, and as we can see, we're having rectangles around the suitcases that are being detected. And you'll get a final output video with the frames all combined together in one video. As we can see, there's still a problem with having multiple rectangles around one suitcase. So I'd say that it requires more, having like tuning those geometric type operations. And if anyone's interested, it would be a really cool thing to maybe take this code and have it as like a computer vision project where you can actually fix up those rectangle issues. And also the current code, there's stationary code for basically what should happen is if a box is stationary, there should be a red box around it. And currently the code is not supporting that. So if you guys want, you guys can take this code and try to refine it and build your own computer vision application or project revolving this idea.
By the way, is everyone able to get this part running? Let us know if you can't get to run.
And after you're done running this, I'd recommend clearing the output of this cell because it may take up a lot of the memory in the actual notebook. So it may be hard to reopen the collab if you ever go back to it. But of course do that after the cell runs because you'll get a video out of it, and that video will be, it'll show the frames all put together.
Can we go into the process frame?
Which part?
Process frame.
Process frame. This part?
Yeah.
And by the way, if you have the syntax errors, it should be like this. So just to underscore by the comma, and you should be good.
What's the duration of the video file?
40 seconds.
Yeah, the video is only 40 seconds.
Is there a reason why like output to API instead of like
There's no reason for that. I think you can do MP4 AVI, whichever you want. I think it's Colab is a bit slow on memory and stuff, so I think AVI worked, so we went with that. This, yeah.
Alright, so that will be it for this M on Monday. So a few things before we close. How do you put it again? So if you guys still need the code, it's right there if you want it. So we have a biotech collaborative event on the topic of LLMs on March 13th. Definitely try to go if you're available or you're interested in biotech. And also, AIS is hiring operations officers. Is this
Yeah.
So if you enjoyed this workshop and you want to be part of the team, the operations team, and work on workshops similar to this in some capacity, feel free to sign up and try your chances on being an officer for AIS. All right, so Mark, you and I.
Yeah, so also on April 19th and 20th, we'll be doing Hack AI, absolute greatest AI hackathon ever. And make sure you apply for that. The QR code's there, also hackai.org, also there. Yeah, it's gonna be a lot of fun. Make sure you apply earlier. Earlier the better. Yeah. I'm not very good at advertising.
Alright. Hey, how many of y'all are like sophomores or juniors? Okay, a fair bit of y'all. How many of y'all are like looking for like jobs or internships?
Yeah, we'll have sponsors there.
Yeah, we'll have sponsors there, and with any hackathon, it's always good to get experience. And you can even put it on your resume. Just say like, "Hey, I went to this hackathon. I got first place. I won this prize and all this stuff." And it's just something good to have on your resume if you do well. So definitely consider applying if that's what you're looking for.
Yeah. Companies like Project.
Yeah. And here's another attendance QR code in case you guys need it. And yeah, that should be it. And thank you guys for coming.
Thank you. I'm just curious, did anyone actually get the output video out? Okay. Okay.
I did the stuck one, like the link for like if you got stuck, and I just like clicked through it instead of actually typing it. but I clicked run all, and like it was running the last cell for like the entire.
Yeah.
Yeah. Bro, is it just me or is it like cold? Huh? Is it cold in here?
Yeah, it is.